So let's say that we have the graph of a function y is equal to f of x, right? Now we want to find the value of our output at x is equal to 2. So when x is equal to 2, what is the value of f of 2? Right, we can easily determine this from our graph. So when x is equal to 2, we see that we have this corresponding point, and the output will be 3. So the coordinate of this point is 2, 3. That means that when x is equal to 2, our y value, f of 2, is equal to 3. Right, so f of 2 will be equal to 3. Now, what if we're asked instead to find the value of a if f of a is equal to 2? So now in this case, our output is clearly given. Our output is 2. But at what values of a is f of a equals to 2? So now we can see this from our graph. So when y is equal to 2, we have this corresponding point, and we also have this corresponding point. Right, so we can tell the coordinate of this point as 0, 2. So when x is equal to 0, y is equal to 2. So that means that one of our a values will be equal to 0. And at f of 0, we have 2. So this is one of our answers. But for the other point over here, we see that we have, for some value of x, or for some value of a, let's say our x coordinate here is a, our y coordinate is 2, right? Now it isn't easy to find out, or it isn't straightforward to find out the value of a just by looking at this graph. So what we can do is we can see that this coordinate lies on this straight line that is negatively sloped. So the gradient of this line is negative. Now what we can do is we can find the gradient of this line. So to find the gradient of this line, that is between this point 3, 0 and this point 3, 3. To find the gradient, we can have m is equal to y2 minus y1 over x2 minus x1, right? So let's consider these 2 points. So we have one point is 2, 3 and another point 3, 0, right? So let's say that this is our x2 and this is our y2. Similarly, this is our x1 value, this is our y1 value. So substituting these values into this equation for our gradient, so this is for our gradient of a straight line or the slope, right? So substituting these values, we have 0 minus 3 over 3 minus 2. So this gives us minus 3 divided by 1, we have minus 3. Right, so our slope is minus 3, which makes sense because our slope is going downwards, meaning it should have a negative slope. So we have minus 3. Right, so we see that our m is equal to minus 3. Oops, I got rid of the graph. So we see that m is equal to minus 3 right? So now what we can do is we can find the equation of this straight line between these 2 points. So between these 2 points, we can find the equation of our straight line. And we can find the equation of our straight line by using the point slope form of a straight line. So the point slope form looks like this. We have y minus y1 is equal to m times x minus x1. Now we can consider, for the values of y1 and x1, we can consider any point that lies on the straight line. So let's consider this point. Let's consider this point. So we have y minus 0 is equal to m, which is minus 3, times x minus x1, and we know x1 is 3, right? So this gives us y is equal to minus 3x plus 9. So this is the equation of our straight line, right? Now we want to find the value of a at which y is equal to 2. So we just have to substitute this value of y into this equation. So we have 2 is equal to minus 3x plus 9. So we have 3x is equal to 9 minus 2. We have 7. Dividing both sides by 3, we get our value of x to be equal to 7 by 3. So this is our x value. So we know that when x is equal to 7 by 3, so f of 7 by 3, this gives us 2. Right, so in this case, we found from previously that one of our a value is 0, but the other a value will be 7 by 3. So these two are our values of a. So this point is 7 by 3. Right, so now if we are given the graph of some sort of equation, right? If we have the graph of some sort of equation, how do we determine if the graph of this equation is that of a function, right? So if we have, say, the graph of something like this, how do we know that this is the graph of a function? We can figure out that this is the graph of a function by applying something called the vertical line test. Right, so we can use something called the vertical line test. So this is basically when we just draw a vertical line straight down the graph at every value of x. Right. So let's say this is at x is equal to a, or this is at x is equal to b. Now, if these vertical lines at every value of x only intersect once through the graph, so if it crosses the graph only once, then this is the graph of a straight line. So we can see that when x is equal to a, this vertical line only passes through the graph of this function only once. So at this point, we only have one intersection. So this means this is the graph of a function. Similarly, when x is equal to b, we have this vertical line going through the graph at only one point, right? So what does this mean? If we think about the definition of a function, we know that for only a single input, say we have x1 as an input, this should only correspond to a single output, y1, right? Similarly, for some other value, if we have x3, then this should only correspond to some single output y3, right? If we had one value of x that gives us multiple values of y, so for one value of x, we're getting multiple outputs, say we're getting y1 and y2, right? Then in this case, this is not satisfying the definition of a function any longer, right? For one input, if we get more than one output, then that is not a function. So let's take a look at the graph of a circle, right? So let's say we have the graph of a circle, right? So now let's apply the vertical line test to this. Let's draw a vertical line through some values of x. So this is x is equal to a. Similarly, let's draw another vertical line, and let's say this is x is equal to minus a, right? So now let's consider x is equal to a. We see that this vertical line passes through our graph at this point as well as this point, right? So what does that mean? So for one value of x, this corresponds to this value of y as well as this value of y, right? So for one input, we're getting two outputs. Similarly, for x is equal to minus a, right, we have one output and another output. So that means this is not the graph of a function, right? So if the vertical line crosses or passes through more than one point of our graph, then that is not the graph of a function. Right, so now let's say we have the graph of some function like this, right? So let's say we have this function, and the graph of this function resembles this, right? So it's some sort of parabolic function. Now, if I wanted to graph the function y is equal to minus f of x, right? So what is happening here? So we find the value of f of x, and each of those values then get multiplied by some negative number, -1 in this case, right? So for this graph, for every output, we are multiplying it by -1, so those outputs become negative. So all of the positive outputs for this graph, all of those outputs will be negative for this graph, right? So if this is the graph of y is equal to f of x, we can graph y is equal to minus f of x by reflecting the graph of y is equal to f of x along the x-axis. So we just reflect this graph along the x-axis to get the graph of y is equal to minus f of x. So this is the graph of y is equal to minus f of x. So if the point a comma f of a, if this point exists on the graph of y is equal to f of x, then similarly the point a comma minus f of a will exist on the graph of y is equal to minus f of x. Right. So let's say this is the point 2 comma 4. Then similarly, this point on y is equal to minus f of x will be the point 2 comma minus 4. Right. So we're just reflecting the graph along the x-axis. Similarly, we consider the graph of another function y is equal to f of x. Now we want to graph y is equal to f of minus x. Right. So in this case, in order to graph this function, we just reflect the graph of this function along the y-axis. So if we have the graph of a function like this, so this is the graph of f of x, then to graph y is equal to f of minus x, we just reflect this graph along the y-axis. So if we were to reflect it along the y-axis, we would get a graph that looks like this. Right. So this is just a reflection along the y-axis of the graph y is equal to f of x. So if the point a comma f of a exists on the graph of y is equal to f of x, then similarly the point minus a comma f of a will exist on the graph of y is equal to minus f of, that's wrong. Similarly, this point will exist on the graph of y is equal to f of minus x. Right, so this is just a reflection along the y-axis of y is equal to f of x. Right, so let's say we have a graph of f of x is equal to x minus 2 whole squared, and that gives us this graph. Then the graph of f of x is equal to minus x minus 2 whole squared will be a reflection along the y-axis, which will look like this. Right, so now similarly, let's say we have another function y is equal to f of x, and then we have another function y is equal to 2 times f of x. Now how do we graph this function? So let's consider a parabolic function once again. And let's say we're dealing with the point 2 comma 4. Right, so this is the graph of f of x. Then if we were to graph this function, all we would do is multiply each of the points, or multiply each of the y coordinates of the original graph by a factor of 2. Right, so this graph is just scaling this graph vertically by a factor of 2. So we will get a new graph that looks like this. Right, so this is just the graph of y is equal to f of x that is scaled vertically by a factor of 2. So if this is the point 2 comma 4, then this point is going to be 2 comma 8, right? So we just multiplied the y coordinate by 2, right? So this is, we just scaled y is equal to f of x by a factor. So if we had the graph of a times f of x, if we were to draw in general this graph, then we would have to scale y is equal to f of x by a factor of a vertically from the x-axis.